So, announcements-wise, there's not that much to announce. The chapter 21 homework. Why do I have that up twice? Is due Friday the 26th on WebAssign. I don't know why I posted that twice. But we'll report. The lab 1 report is due today, and there's a lab today at 1 o'clock. Lab 1 report, everybody already turned it in, so yeah. Yeah, you need to make it up at some point. You gotta set up a time with me to make it up. You were excused. Talk to me after class about that. Yeah. So we were talking about earthquakes and things that can come from earthquakes. And one of the more dangerous things that can come from earthquakes is a tsunami. When there's an earthquake underwater, one of the things that can happen is you can get a tsunami, a massive wave, which can be extremely destructive. And well, out to sea, tsunamis aren't very dangerous because waves get bigger the shallower the water they're in is. So out to sea, tsunamis are very fast, but they're not very high, and they're very long wavelength. So you just go up and down. But when you get close to shore, they slow down, their wavelength shortens, and they pile up much higher. And that's when they get really dangerous. And tsunamis can be incredibly destructive. If the source of the tsunami is far away from you, you have some time to react. There's actually a system of sensors out in the Pacific Ocean to track tsunamis because they travel across the Pacific Ocean. But if the source is close to you, then you're screwed. So the recent Indonesian tsunamis were unfortunately the earthquakes were just off the coast. So there was very little that could be done about it. It is? So here's a short video clip about tsunamis. And the most common cause of tsunamis is understood.
There are more tsunamis in the Pacific Ocean than any other. So in 2004, the world was taken by surprise when one of the largest recorded tsunamis of all time took place in the Indian Ocean. On December 26, 2004, Indonesia was rocked by the second largest recorded earthquake ever, 9.2 on the Richter scale. Minutes later, a 90-foot tsunami slammed into the Southeast Asian coastline. 225,000 men, women, and children lost their lives.
The Indonesian earthquake had as much energy in it as the total energy consumption in the United States in 1 year.
This enormous burst of energy had been released in just seconds. Once again, the world had been reminded of the Earth's awesome power. In the last 50 years, scientists were finally able to confirm a solid link between earthquakes and tsunamis. Although the Earth may seem to be a solid sphere, beneath the oceans and continents it is divided into 8 major and many minor segments known as tectonic plates. Where they meet, they can grind and jostle against each other at fault lines, causing earthquakes. Geologists had long thought that the Cascadia fault line was incapable of generating a major quake. But Atwater's investigation has proved that it was highly active. The big worry for Atwater and the thousands of people who live in this region is that the Cascadia fault line bears an uncanny resemblance to another highly active fault line, the Sunda megathrust. It was an earthquake along this fault that was responsible for the Indian Ocean tsunami that killed nearly 250,000 people.
Where we get 2 tectonic plates coming together, such as in the case of the Indonesian tsunami in 2004, one plate pushes beneath the other plate and creates lots and lots of friction and tension and drags the upper plate down with it. And that process can take hundreds of years, even thousands of years. It's a very slow process. But eventually, the pressure of this one trying to push back up again wins, and it flips like that. And that creates a megathrust, a sudden movement of the seabed. And that's what creates a phenomenal tsunami.
And so tsunamis are most commonly caused by earthquakes, but they can be caused by other things, volcanic explosions, massive landslides, things like that. And there's some really odd recent ones where there was one recently that was trapped in there was like a massive, there was a landslide that set off a tsunami in like a fjord, in like a thin bay, and it resonated in that bay at the same frequency for like weeks. So when plates come together, tremendous forces are involved. And they can result in the buckling, fracturing, and shifting of rock units. So the crust can deform, and these forces can rupture the plate hedges into huge displaced blocks that can eventually result in the formation of mountain ranges. And there's basically 2 types of deformation that can occur. Either you can bend or you can break. Those are folding and faulting. Folding is when the layers of rock fold, and faulting is when the layers of rock slide along cracks. So folding is the buckling of rock layers into anticlines, which are arches, and synclines, which are troughs. So anticlines are arched over like the top of an A, and synclines are troughs, the opposite. And folding occurs when there is slow compressive force that applies extreme pressures on the rock layers. So folding is more common when there's very high force but slow speed, and also at deeper depths, because some of the additional forces that occur deep underground help prevent faulting and promote more in the way of folding. And the forces that cause folding can be exerted horizontally. You could be squeezing the crust, or vertically. And in general, folding occurs mainly during the early stages of mountain building. You bend before you break, is a way you can think about it. You get folding before you get faulting. So here are some examples of folded terrain. The surface topographic features are not always going to match the underlying folding, because it's, a rock layer's resistance to erosion and other factors that determines what sort of topographic features are formed. So anticlines don't always form high ridges. You can have a ridge here on an anticline, but you can also have a ridge in a syncline. Where it could be that the raised up layers that would have been lower are easier to erode, and so the trough stays remaining. There's a lot of factors involved. Faulting. A fault is a fracture in the rock along which there has been visible movement of the two sides relative to each other. If there isn't visible movement, it's called a joint. And you can have faults with stresses. There's basically three ways you can have faults. You can have compressional faults, forces coming together. You get, if you have vertical compression, you get uplifts. You have horizontal compression, the crust gets shortened. You can have tensional faults, stretching forces. This causes the crust to lengthen. And there are also faults that slide side to side, which neither lengthen nor shorten the crust, but sideways, transform movement. So a fault plane is an approximately planar surface along which the movement takes place. The fault is basically a big crack. The crack effectively is a plane through the three-dimensional rock. And all the terminology for faults comes from mining, because a lot of valuable mineral deposits are along faults, because if you have a fault, material can seep into the fault and deposit. So a lot of valuable mineral deposits are deposited along faults where material has seeped in and deposited out. So we're often following along a fault in like a gold mine or a mine for some valuable mineral. So the two sides of a fault are called the hanging wall and the foot wall. The hanging wall is the one that's on top. The foot wall is the one that's on bottom. It's called the hanging wall because you hang stuff on it. And the other one's called the foot wall because that's where your feet go. So this is the uppermost side of an inclined fault plane is the hanging wall. The foot wall is the lowermost side. And the fault block that has moved up relative to the other side is called the upthrown side. In compression, the hanging wall moves up. In tension, the foot wall moves up. So there's three basic types of faults. There is a normal fault, which is caused by tension, pulling apart. The hanging wall moves down with respect to the foot wall. So the upthrust wall is the foot wall. Tensional forces cause normal faults. So when you're stretching things apart, you get what are called normal faults. The opposite of a normal fault is a reverse fault, where the foot wall moves down with respect to the hanging wall. So the hanging wall is upthrust. Compressive forces cause reverse faults. If a reverse fault is very shallow, it's called a thrust fault. That previous video mentioned the megathrust. That's the really big thrust fault where one plate is subducting under another. And then lastly, there are strike slip or transform faults where the stresses are parallel to the fault plane. Neither side goes up, they go sideways. And there are technically combinations that are called dip slip faults, but you don't need to worry about those. So here are the different types. So if you have a fault, this is the hanging wall, this is the foot wall. The hanging wall is on top of the foot wall. This is the fault plane. If the hanging wall goes down and the ground gets longer, that is a normal fault. The hanging wall goes up and the ground gets shorter, that is a reverse fault. If you have a reverse fault that's very shallow, where you can get layers, lower layers on top of older layers like this, that's a thrust fault. And if the movement is side to side and the hanging wall on the footwall, neither one goes up or down. That's a transform or a strike slip fault. And then there's technically a combination of one of these. It's called a dip slip fault. It's transform and either normal or reverse. So here is a short video about the types of faults and what they're caused by.
Hello everyone, this is Earth Science teacher Tim Martin, and in this video I want to introduce you to the geologic concepts of folding and faulting. When we look for faults and folds in the Earth, what we're really doing is looking for past evidence of plate tectonic motion. Let's take a minute to review the basic motions of plate tectonics. The first of the three motions is divergent motion. This occurs when magma comes up from deep within the Earth. This typically happens in the middle of the ocean. It generates earthquakes as the plates move apart from each other. This may also happen on continental plates as well. The next type of motion, convergent motion, happens when plates collide. Here we can see an oceanic plate subducting beneath a continental plate. As the plate subducts, it cracks and breaks, generating earthquakes. Finally, we have transform motion. This occurs where two plates slide or grind past each other. Again, this generates earthquakes. Now let's take a look at the structures identified with each of these three types of motion. To start off with, let's talk about rifts or cracks. When the Earth is pulling apart or forces are acting on it in opposite directions, the crust will thin, stretch, and possibly crack. These cracks are often known as rifts. This is caused by tension or divergent motion. A normal fault also happens with tension or divergent motion. If the rock is more rigid and less likely to stretch, it may simply crack, and when it does, one block may drop lower than the other. This is what's called a normal fault. Opposite the normal fault, we have a thrust or reverse fault. This occurs from compression or convergent motion. When two plates are pushing against each other, one plate may go down or another one may go up. This creates a thrust or reverse fault. Finally, a transform fault, or a strike-slip fault, occurs with lateral stress. When two parts of the Earth's surface are moving in opposite direction with respect to each other, one may slide, causing a transform or a strike-slip offset. While sometimes rocks break with faults, sometimes they're soft enough to fold. A fold occurs with compression or convergent motion. Sometimes rock layers may fold with an upward bend, other times they may form with a downward bend. Both types of folds occur with compression or convergent motion. An upfold is referred to as an anticline. The downward or U-shaped fold is referred to as a syncline. Let's take a look at what this looks like with real geology. Can you identify the motion from these real images? Let's take a look at these 5 different features. Thingvellir National Park in Iceland is one of the classic locations where the Earth is splitting apart. On the right-hand side of the picture, we see the North American plate. On the left side, the European plate. As the plates are splitting apart, this rift or gap is opening up. This occurred through divergent motion. This picture of the Hayward Fault was taken in Fremont, California, in Central Park. You can see when the road planners built this road, they didn't intentionally offset the sidewalk and curbing. What happened here is part of the road was built on the North American plate, and the other part of the road was built on the Pacific plate. Here's the fault line, and we can see the further section is moving northward, where the side that the photographer is standing on is moving towards the south. Moab Fault is a dramatic fault that was revealed in a road cut just outside of Arches National Park in Utah. Here we can see several very large faults. As we identify the previously aligned layers, we can see that this brown stripe used to all be the same layer, but now has been offset with several normal faults. This represents divergent motion or tension. Browns Canyon of the Arkansas River goes through Salida, Colorado. Here we can see rock layers that have been folded. This must have occurred through compression or convergent motion. It's impossible to make a fold by pulling. Going from a large scale to a rather small scale, In Mosaic Canyon in Death Valley National Park, California, we can see this small layer was offset, the fault indicated in red, and these yellow layers are offset with a little bit of overlap. This indicates that this was a reverse fault caused from compression or convergent motion. So let's take a little quiz. Can you identify the motion in these next 5 images? Feel free to pause the video between each image. Number 1 is Katobe Knob, located in the Cedar Mountain Recreation Area in the San Rafael Swell in Utah. Number 2 is a rock structure that I found at Noosa Heads in Queensland, Australia. Number 3, a road cut near Orderville, Utah. Number 4, rock layers west of Wild Rose Campground on Wild Rose Road in Death Valley National Park. Number 5 is specifically called Earthquake Fault, located just outside Mammoth Mountain Ski Area in Mammoth Lakes, California. So, could you identify all 5 of these images? What sort of plate motion caused each? Are they normal faults, reverse faults, folds, or rifts? Let's take a look at each. Number 1, Katobe Knob in the San Rafael Swell in Utah. First, we identify the fault plane, located here. Then we identify the layers that used to line up, here and here. So we can see, because of the overlap, this must have formed from compression or convergent motion. Number 2, Noosa Heads in Australia. Again, the first thing to do is identify the fault plane, located here. Then the layers that as they used to match up, here and here. Because of the lateral offset, we understand this must have been transform or a strike-slip fault. Number 3, again, this is a road cut in Orderville, Utah. Let's identify the fault plane, leaning from left to right across the image. See the double brown lines towards the bottom of the image? These used to match up with each other. Thus, this is a normal fault, formed through tension or divergent motion. Number 4, along Wild Rose Road in Death Valley National Park. We can obviously see folds. These folds must have formed from compression or convergent motion. Finally, number 5, the earthquake fault near Mammoth Lakes, California. Again, this is a great example of a rift where the earth was experiencing tension and cracked open, causing this split in the rocks. Would you like a little more practice identifying folds and faults? You can download a slideshow of images that I've taken from around the world of places where we can see convergent, divergent, and transform plate motion. Thanks for watching, and I hope to see you again on another Team Art Science video.
So actually, I slightly misspoke earlier. Dip-slip fault is a transform or a normal fault. The combined version is called a hybrid. You don't need to know that term for the test or anything. It's just, I didn't want to give you wrong information. So, mountain building. Mountain building occurs most often and because of converging plate boundaries. The most common place you get new mountains are when plates are coming together. And there's 3 broad categories of mountain formation. There is volcanic mountains formation, fault block mountain formation, and fold mountain formation. Volcanic mountains occur where one plate subducts under another. When it subducts, it melts. And as it melts, magma is released, which rises up and forms volcanoes, series of volcanic eruptions. It can also form underground igneous rock, large underground igneous rock structures, but you get volcanic mountains that are formed from volcanoes, so a series of volcanic eruptions. Most volcanic mountains occur along convergent boundaries. So the most common way is where along an oceanic convergent boundary, you get a chain of volcanic islands because the subducting plate is melting and volcanoes are formed. So examples of these are the Aleutian Islands, Japan, the Lesser Antilles. These are all examples of volcanic mountains. You can see them surrounding the Pacific Ocean. Now, when you have an oceanic plate subducting under a continental plate, you also get volcanic mountains. They're a little different. But along the continental oceanic convergent boundary, you get volcanic mountains like the Andes. In fact, this type of mountain building is called Andean mountain formation, because the Andes are the standard example. So the continental plate will always overlie the subduction zone, and so this is where the volcanic mountains will form. So the Andes Mountains of South America, as well as the Oceanic Nazca, were formed as the Oceanic Nazca Plate is subducted beneath the continental South American plate, and the Cascade Mountains are also volcanic mountains. So the Cascade Mountains up in Washington and Oregon are formed as the small plate up there subducts against the North American plate. You can also in things like the Andes, you get these large igneous rocks formed underground where the magma never makes it to the surface, but it can still help form the core of mountains. So here are the Cascades in Washington. These are volcanic mountains. You get volcanoes there. Sometimes they explode, like Mount St. Rushmore did. Now, fault block mountains are one of the ones where they're produced not by compression, but by tension. So normal faulting can produce tilting and uplift of large blocks of crust, large crustal blocks, and you can get dramatic fault block mountains rising abruptly above the surrounding lowlands. So some examples of these are the Grand Tetons in Wyoming, the Sierra Nevada mountains of California, and the Wasatch Range of Utah are all examples of fault block mountains. You can also get upthrust areas from reverse faulting. So here's Mount Whitney. A very, right angle sort of top, asymmetric sort of top. Now, fold mountains are characterized by prolific folding of the rock strata. These are places where two continental plates slam together. They have nowhere to go, so they bend and buckle. So the Alps, the Himalayas, the Appalachians are all examples of fold mountains. The Alps and the Himalayas are much younger than the Appalachians, but they're all fold mountains. They're also characterized by thick packages of marine sedimentary strata. What happens is that as the two continental plates converge, the marine sediment that was in between in the ocean gets scraped up and piled up. And that is the middle of where the two plates combine. So that gets pushed up and forms the tops of the mountains. So it was originally deposited below sea level, then uplifted and incorporated into the fold mountains. So marine fossils are regularly found high in a fold mountain range. So you can go to the top of the tallest mountains in the world and find marine fossils, like shells and various things like that. Here are some fold mountains in Alberta, Canada. You can see the layers, the folding layers up there. So the most recent fold mountains in the world are the Himalayas. So during the breakup of Pangaea, about 200 million years ago, the subcontinent of India broke away from Africa. As the Indian plate moved north towards Asia, the oceanic lithosphere was continually subducted beneath Eurasia. And during the time before those two continents collided, sediments were deposited in the marine waters between India and Eurasia, because there was stuff going on dumping sediment in the water. Had millions of years to do this. So eventually, the Indian plate moved north, slammed into the Eurasian plate, pushed up the Himalayas and the Tibetan Plateau. So the sedimentary strata that was deposited between Eurasia and India was eventually uplifted and folded into the mountains. And when the continental crust portions finally collided, the subduction significantly slowed. The edge of the Eurasian plate was uplifted as the continental Indian plate was wedged underneath it, leading to the Tibetan Plateau, and the Indian plate continues to move north today, resulting in continued uplift of the Himalayas and the Tibetan Plateau. The Himalayas are getting taller. So you have marine strata in between the continental plate, the other continental plate. That marine strata gets scraped off over time, piled up, and then forms the top of the Himalayas. So that was the end of chapter 21. So I'll do a quick review, and then we'll start on chapter 22. So the two types of seismic waves are surface waves and body waves. And the earthquake waves responsible for the most damage caused by earthquakes are surface waves, because they affect the surface water. The two types of body waves are P waves and S waves, primary waves and secondary waves, or pressure waves and shear waves. Both P waves and S waves can travel through solids, while only P waves can travel through liquids. Basically, pressure waves can travel through whatever. They could travel through gases as well, but they'll lose a lot of their power there. But they could also travel through solids and liquids. P waves travel faster than S waves. And by measuring the difference in the time between their arrival, you can figure out how far away the source of the earthquake was. And the velocity of body waves depends mainly on what physical property of the material they pass through, primarily the density. The denser the material, the faster they travel. The four layers of the earth from the surface to the interior are the crust, the mantle, the outer core, and the inner core. All the layers are solid except for one. Which one? The outer core is liquid. Which is thicker, continental or oceanic crust. Continental crust is thicker. It's made of more granite-like minerals, while oceanic crust is thinner and made of denser, more basalt-like minerals. So continental crust is mainly composed of what type of rock material? Granite, or felsic rock. Oceanic crust is mainly composed of what type of rock material? Basalt or mafic rock. The boundary between the bottom of the crust and the upper mantle is called the Mohorovic discontinuity, or just Moho. The solid, rigid layer of the crust, or of the crust at the top of the mantle, is called the lithosphere. The layer that lies below the bottom of the crust that makes up the upper mantle is the asthenosphere. This is the softer, more easily flowing. So there's the lithosphere, which is the crust and a bit of the top of the mantle. And then beneath that is the softer layer, the asthenosphere, that it moves on top of. The movement of the continents over time from one large supercontinent to their present positions is referred to as the theory of continental drift. And to our best understanding, this has happened multiple times in the history of Earth. The name of the supercontinent that broke up around 200 million years ago is Pangaea, which means all land. The name of the scientist that proposed the theory discussed in question 16, proposed continental drift, was Alfred Wegener. And the three pieces of evidence used for continental drift were biological and paleontological evidence, mineral evidence, and the shape of the continents. And there was also glacial evidence, but like continuity of geologic features and glacial evidence, biological and paleontological evidence, and then the continents fit together. Those were the three main things. And the theory of continental drift was not generally accepted by the scientific community because it had no clear mechanism to explain the process of continents moving. That didn't come around until 1960. The name of the geologist in the 1960s that used ocean floor soundings to propose the theory of seafloor spreading was Harry Hess. This was based on the work of other people, including of a number of other people. And what has happened to the magnetic field of the Earth several times in the past that's recorded in the rock material bordering the mid-Atlantic ridge, the magnetic field of the Earth is regularly reversed. And the theories of continental drift and seafloor spreading have now been combined into the single theory of plate tectonics, which is older, continental crust or oceanic crust. Continental crust is older. Oceanic crust is constantly created and destroyed. How many plates are thought to exist? Around 20. Most volcanic and earthquake activity occurs at the edges of plates, the borders between plates. The three types of plate boundaries are convergent, coming together, divergent, spreading apart, and transform, sliding side to side. The layer the Earth's crust rides on is the asthenosphere, the soft upper part of the mantle. Plate movement is being believed to be caused by convection currents in the Earth's upper mantle. Two plates moving apart is referred to as a divergent boundary. And at a divergent boundary, where is the youngest rock found? It's found near to the boundary because new rock is formed at the divergent boundary as the plates separate and magma wells up. Two plates moving towards each other is referred to as a convergent boundary. That's where plates are converging and combining. The three combinations of convergent boundaries are oceanic-oceanic, or two oceanic, where oceanic crust meets oceanic crust, and one subducts under the other. Oceanic continental, where oceanic crust meets continental crust, and the oceanic crust subducts under the continental. And lastly, continental-continental, where two continental crusts meet each other and fold and pile up to form mountains. So which of the plate combinations doesn't show much subduction? That's continental-continental. Because the continental crust is too thick and too too light. It floats too high, basically. The type of crust that always subducts is oceanic crust. Deep sea trenches form in oceanic-oceanic combinations, and also at the less dramatically at oceanic continental. The combination of plate movement that results in very high mountain ranges, such as the Alps, that's continental-continental convergence. The type of plate boundary that involves plates moving past each other is a transform boundary. That's a fault you get faults like the San Andreas Fault. Which type of boundary do most volcanoes form? Divergent, convergent, or transform? Divergent and convergent. You get volcanoes at both of those. I think the majority of volcanoes might be at convergent boundaries. Definitely the majority of volcanoes on the surface that we can see are at convergent boundaries, because most divergent boundaries are underwater. Most earthquakes form because of the movement of continental plates. A fracture of rock caused by visible movement of the plates is a fault. The longest fault systems are at transform boundaries, where things are sliding past each other. The actual point in the Earth's interior where an earthquake originates is called the focus. The point on the Earth's surface directly above that origin is called the epicenter. And there will be questions about the difference between focus and epicenter on the test. The device used to detect and measure earthquake waves is a seismograph. The earthquake scale that measures earthquakes by the energy they release is the Richter scale. The modern version is called the modified magnitude scale, but it's the Richter scale. The earthquake scale measurement that measures earthquakes by the damage they cause is called the modified Mercalli scale. An earthquake on the ocean floor can produce a giant wave called a tsunami. Mountains are usually formed when crust is deformed through folding and faulting. Arch-shaped folds are called anticlines. Trough-shaped folds are called synclines. The kind of fault that forms when two sides of rock formation are pulled apart is a normal fault. The kind of fault that forms when two sides of a rock formation are pushed together is called a reverse fault. And the kind of fault that forms when two rock structures slide by each other is called a transform or straight slip fault. Besides being formed from faulting and folding, mountains can also form from volcanism, from volcanoes. So that's chapter 21. And because chapter 22 is kind of long, I'm going to get started on it. Apparently, I'm going to have to deal with this real quick. Let me just do this, so that will fix the problem. So, chapter 22 is on minerals, rocks, and volcanoes. So we're going to talk about what minerals are, how minerals work, how they form, and then we're going to talk about we'll talk about the various types of rocks, how they form, and one of the ways that they form involves volcanoes, so we'll also discuss volcanoes. So we'll define the characteristics of minerals. We'll look at the formation of minerals from magma and other solutions. We'll look at the physical and chemical tests that can be used to identify minerals. We'll talk about how to use crystal form, luster, hardness, cleavage, and fracture, streak, special properties, texture, and density or specific gravity to identify various minerals. We'll describe and give examples of common mineral groups, including silicates, carbonates, and oxides. And we'll talk about the usefulness of various minerals, including ores and gems. We'll look at the various processes involved in the rock cycle and discuss the conservation of matter during formation, weathering, sedimentation, and reformation of rock materials. We'll talk about how the composition of magma influences the formation of igneous rocks and look at the factors that influence how igneous rocks melt and crystallize. And we'll describe the different types of igneous rocks in terms of mineral composition and texture. And we'll look at the relationship between magma cooling rates and grain size. We'll talk about the types of volcanoes, shield, cinder cone, and composite volcanoes in terms of their formation and their type of eruption. We'll look at the types of magma found in volcanoes and how magma type influences volcanic eruptions. We'll look at the role of pressure and dissolved gases in volcanic eruptions. We'll look at the types of materials expelled during a volcanic eruption. We'll describe the processes involved in the formation of sedimentary rocks. We'll look at the main structural features of sedimentary rocks and how these features can provide clues of past life on Earth, because sedimentary rocks preserve historical information very well. And we'll look at the formation of clastic or inorganic sedimentary rocks in terms of grain size, and we'll look at the formation of chemical and biochemical sedimentary rocks. And then lastly, we'll look at the various types of metamorphism involved in the formation of metamorphic rocks and the characteristics of foliated and non-foliated metamorphic rocks. Now, if you'd like to get a better feel of the stuff we're going to discuss in this chapter about mineralogy and how rocks move, I could suggest watching the anime Ruri Rocks, which is just finishing up its season on Crunchyroll. It has some excellent descriptions of the processes involved in the rock cycles and how minerals move, and how minerals are formed and things. And it focuses on shiny rocks, pretty much explicitly. It focuses on, attractive crystals, but involves actual characters who are actual geologists. So, good show. It's on Crunchyroll, and if you don't have a Crunchyroll subscription, I'm certain there's other ways you can get it. And I'll leave it at that. So, minerals, rocks, and volcanoes. So in this chapter, we're going to largely talk about rocks and minerals. We'll talk about what the difference between a rock and a mineral is. We'll see that specific rocks and minerals form in response to a myriad of Earth processes. So the rocks and minerals you see tell you about the conditions in which they were formed. So existing rocks and minerals can be used to determine past geologic events because they effectively reference the conditions that they formed. So, what is a mineral? So, a mineral is basically what rocks are made of, the base material that rocks are made of. But a rock can be made of multiple minerals. So, a mineral is a naturally occurring, inorganic, crystalline, solid substance consisting of one or more chemical elements in fairly specific proportions with a distinctive set of physical properties. So a mineral is a specific material you find in rocks that occurs naturally. It forms crystals, and it's not produced by living things. So things that aren't minerals are, if you made it in a lab, it's technically not a mineral. If it came from a living thing, it's usually not a mineral. So like amber is not a mineral, or coal is not a mineral. That gets a little fuzzy because sometimes we consider things that are primarily made. It gets a little fuzzy there's a whole category of stuff called mineraloids, which are things that are not technically minerals, but are very close. And then lastly, it has to be naturally occurring. It has to not come from a living thing, and it has to be crystalline. So actually, the other exception is something like obsidian, which is a glass, is not crystalline. And so that is technically not a mineral. And now a rock is something that is made of one or more minerals. And it's made of a bunch of crystals of various minerals generally. And minerals are around us everywhere. Some are very valuable, things like diamonds, sapphires, and emeralds. They make nice gems. Gold is a mineral because gold actually naturally occurs just as gold. Metallic gold just exists in the ground. And other minerals are very common, things like calcite and quartz. Calcite's what limestone is made of. Quartz is what most sand is. Quartz is probably the second most common mineral on the surface of the earth. And mineralogy is the study of minerals. And we'll also talk about certain rock types as ores as being rich in minerals. When we talk about an ore, that means that is some rock that you can get a commercially viable quantity of something from. So iron ore, gold ore, or copper ore, those are rocks that you can get an amount of iron, gold, or copper from that is worth it, worth the effort. The rocks classified as ore have a commercially viable amount of some type of element or mineral, which means that depending on technology and current economics and things, whether or not something is an ore can change. So, you know, you can have something that used to not be considered an ore because it wasn't worth it, and a new technique for extracting the valuable material was developed, and suddenly it is. Or material could go up in price, and thus crappier ore could be more worthwhile. So here are some examples of various minerals. Here's calcite, big crystals of calcite. There's hematite, which is an iron ore. There's limonite, there's gypsum. Which is calcium sulfide. I can't remember what that's on. Gypsum. There's halite. That's rock salt. That's the same thing as table salt. There's the feldspars. There's the plagioclase the calcium plagioclase feldspar, sodium plagioclase feldspar, and orthoclase feldspar. Feldspars are the most common type of mineral in the crust. There's quartz, second most common. Olivine, this is a very mafic mineral. It's closer to what you see in the mantle. Pyroxene, amphibole, biotite, and muscovite. These are both micas. So they make thin sheets. And 8 chemical elements are the major constituents of most of the minerals. There are exceptions, but the majority of minerals are made of these 8 chemical elements. The 2 most common elements in the Earth's crust. So these are the most abundant elements in the Earth's crust. The 2 most common by far are oxygen and silicon. The vast majority of minerals have oxygen in them, and the biggest group of minerals is made of primarily silicon oxide, silicon and oxygen. So the additional minerals that are common, oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. Those are the other common ones. Aluminum is all over the place. Iron is common in lots of places. Generally, if you see a red rock, it's got iron in it. But often darker rocks have iron in them. And then there's calcium, sodium, potassium, and magnesium. Over 2,000 minerals have been identified in the crust, but only about 20 of these are common. And I think it's actually more than 2,000 because geologists keep finding super rare minerals that like only exist in one place, kind of thing. And less than 10 minerals account for more than 90% of the Earth's crust by mass. So here we can see the relative abundance and mass of elements in the Earth's crust. You can see oxygen is by far the most common element in the Earth's crust. 47% of the crust. Another 27% is silicon. So oxygen and silicon account for 74% of elements by mass in the Earth's crust. And that's because silicon oxide, or the silicates, which are primarily made of silicon and oxygen, are the most common minerals in the crust. And then we have the 80, aluminum is 8%, iron is 5%, calcium is 3.5%, sodium is 3%, potassium is 2.5%, magnesium is 2%, and then the 82% other elements make up about 2%. So what time is it? Okay, still have 15 minutes. I'm going to keep going. So the most common mineral group is the silicates. So most minerals that form crustal rocks have significant amounts of oxygen and silicon. The one with the most is quartz. Quartz is just oxygen and silicon. It's entirely composed of oxygen and silicon, and it has the chemical formula SO2. It's silicon dioxide. And quartz and other minerals that contain oxygen and silicon are called silicates. And the silicates are the most abundant family of rock-forming minerals in the crust. And here is a short video about minerals and the definition thereof. Minerals, crystals, and rocks.
What are minerals, rocks, crystals, and gems? What's the difference? Well, to start off simply, rocks, crystals, and gems all can be made up of minerals. So what the heck is a mineral? A mineral is a solid made by the natural activities of Earth, like lava spewing out of volcanoes or water dripping down through cracks in caves. Fluorite, gold, and calcite are just a few mineral names you might recognize. Minerals are made up of elements that come together in a regular, specific pattern. These geometric groups of elements are the building blocks of a mineral. A crystal of that mineral forms when these building blocks stack on top of one another, repeating their arrangement to form a three-dimensional object with flat faces. Quartz, for example, has a crystal structure made of oxygen atoms and silicon atoms that repeat in a shape that looks like a rhombus. The shapes that these chemical building blocks take are different from mineral to mineral. Sometimes, two minerals can be made of the same elements, but with different building blocks making up their structure, like diamond and graphite. The large geometric shapes and flat faces we see in crystals reflect what happens when these building blocks repeat over and over again. Now let's move on to rocks. A rock is a solid object made up of mineral grains, but it can have many different minerals inside it, and you don't see the same repetitive shapes that you see in crystals. Granite is an easy example. You can see the different grains of many types of minerals making up a piece. Limestone is also a rock, even though it's usually made of mostly one mineral, calcite. But limestone is made of calcite fragments mashed all together, and a calcite crystal has order and a geometric shape. So where do gems fit in? They have a geometric shape, and many look like crystals, right? But really, gems are minerals or stones that have been cut, ground, and polished by people to enhance their beauty. A finished gem may look very different from the original mineral it was carved from. Many times, gems are shaped with different flat faces to catch and scatter light. They aren't always minerals either. They can be made of things that come from animals and plants, like pearls or amber, or they might even be man-made in a lab. Let's make like a crystal and repeat that one more time. Think about pyrite or fool's gold. Pyrite is a mineral made of iron and sulfur. Those elements come together in the shape of a cube and repeat to form a pyrite crystal. These crystals can get so big you can see them with your naked eye. Other times, the pyrite crystals are just flecks in a rock like slate. And if it was cut and polished with flat faces, it would be considered a pyrite gem. So there you have it, crystal clear. The difference between minerals, gems, rocks, and crystals.
and, searching for various minerals and attractive crystals or gems is a thing you can do. That's sort of the plot of Rare Rocks. So that they have much better luck than any normal person would have. But yes, so silicate structure is based on a network of, so the silicate structures, turns out when you have silicon and oxygen, it forms a tetrahedral structure, a little pyramid. And these basic building blocks are called the silicon oxygen. So they form a network together. These are the silicon oxygen tetrahedra. If you just have silicon oxygen tetrahedra that are all connected to each other, at all corners, you get quartz. There's nothing else in there. If there's some impurities, that gives you color. So most colors, are through quartz. So you get covalent bonding within the tetrahedron, and the tetrahedrons can bond to each other. And a significant amount of variation occurs in the structural arrangement of these tetrahedra. There's a whole bunch of different ways they can be combined. They can exist independently, just loose tetrahedra with other ions in between, no sharing of oxygen, or they can share oxygens in various ways. So this is sort of a silicon oxygen tetrahedron, silicon in the center with 4 oxygens around. And this, the whole thing ends up negatively charged. So you have other ions in between, or if the oxygens get shared, you can get something like quartz. So in addition to oxygen and silicon, most silicon minerals also contain aluminum and 1 or more other elements. Aluminum is very common, and if that aluminum comes out to form aluminum oxide, you can get gemstones. So sapphires, rubies, and emery are all corundum, which is aluminum oxide. So if you've ever used an emery board, that has on it the same mineral that makes up sapphires and rubies. And the difference between the different types there are the different impurities. So rubies have chromium in them to make them red. Sapphire is a more general term that covers all other colors mostly, and then emery is usually black from iron impurities. And it also doesn't form big crystals, tiny crystals, where we find it. The various silicate minerals result from the different structural arrangement of these tetrahedron building blocks and the different metal ions within these structures. And they can be arranged independently, in single chains, in double chains, as continuous sheets, and in a 3-dimensional network. So you can have single individual tetrahedra floating in between other ions. You can have single chains, double chains, flat sheets. This is what gets you things like mica. Or you can have a 3-dimensional network. 3-dimensional network without significant additional other ions gives you quartz. 3-dimensional network with significant other ions gives you feldspars. So the most common silicate minerals are the feldspars. They're a group of structurally related, the 3-dimensional network minerals that are a set of the most abundant minerals in the Earth's crust. There's 2 basic types. There's the plagioclase feldspars, which have oxygen, silicon, aluminum, and calcium or sodium. And there's the potassium feldspars, which have oxygen, silicon, aluminum, and potassium. And all the silicates will have silicon and oxygen in their formulas. That's what makes them a silicate. So here's a sodium-rich feldspar that's albite. Here's anthronite, which is a calcium-rich feldspar. Here's another feldspar. This is a mica, olivine, quartz, and pyroxene. And they all contain silicon and oxygen along with other elements to form specific chemical formulas. So feldspar has like sodium, aluminum, things like that. Olivine has lots of iron and magnesium, which makes it denser and darker. I think this is probably a good place to stop with the non-silicate minerals. So we talked about the silicate minerals, and all the other minerals in the crust are non-silicate minerals. Most of them contain oxygen, though. So the most common non-silicate minerals are the carbonates, the oxides, and the sulfides. And then there are also things like pure elements like gold and silver, and some gemstones, diamond, ruby, and sapphire also qualify as non-silicates. So I think we'll stop there. I'll see you all at 1 for the lab. And yeah, I'll stop there for today. So